Okay, good afternoon, everyone. I hope that you all enjoyed your lunch. Looking around the room at lunchtime, it was really nice to see it's more or less feeling back to normal these days, and everyone would seem to be really enjoying themselves. So that's always really nice for us, to see after we spend time like fitting meals and stuff that we haven't done in a few years. So I hope that you all have full bellies and you're ready for another great session. We are moving more into the topics on GC GC in this next session, focusing on a few different topics in the area of fuels and vehicles. So I hope that you'll enjoy. Our first talk is from Grant Ochoa from the University of Washington in the Synovec group. And today he's going to be speaking to us about jet and rocket fuel.
Thank you very much, Kate. Yeah, so today I'd like to talk to you about some developing some advanced chemometric tools that we've used in the Synovec group, specifically to get at better characterization of jet and rocket fuels. And in particular, what we're focused on are the analysis of polar compounds and jet fuels. And so to start on, just talking about why we need to work with jet fuels and rocket fuels in the first place. So lots of people use these rocket fuels. Space it's not only limited to space organizations, but also things like defense, such as the Navy and the Air Force. And it's really important that these fuels work as they should consistently. And to do that, we have to have a lot of specifications on things such as polar compounds, sulfurs, oxygens, nitrogen compounds, etc. And because without monitoring these, they can lead to very high buildup of carbonaceous deposits in jet engines, and that can lead to very low thermal performance. And so right now, a lot of the testing that we do for this is kind of slow. There's a whole suite of ASTM methods that need to be run on a fuel before it can be run. But they always get at a very more overall view of the fuel. Like if so less than 500 part per million sulfur or so many aromatics, but we want to try and get to the heart of the matter of like not only what kind of polars may be causing these kinds of issues, but what are the identities of polars, and some polars have worse effect on the deposits than others. As I mentioned, a lot of this has to do with the carbonaceous deposits in the fuel engines, and so while it's been noticed a lot of compound fuels with these amounts of polar compounds may react and form a lot of deposits much faster. It is not, that's kind of just like an overall view. These fuels generally don't get tested afterwards to find the exact nature of what is underlying that methods there. And so moving on, we need to be trying to we want to develop new ways that can characterize at a very base chemical composition method what sort of polar compounds are leading to higher degrees of or lower thermal stability and higher degree of carbonaceous deposits. And so we've done a lot of collaboration with AFRL in this matter, but the main idea of what we're trying to do is build up a lot of chemometric tools that utilize the GC GC-TOFMS information in such a way that we can pull this, attack this analysis in a much more thorough way. And so for analyzing all of our rocket fuels, as we're apt to do here, we like to use our GC GC with a nice Pegasus BT40 that is pretty much been our workhorse. Been lots of our jet fuels on there, and to try and get the most information that we can out of our chemical composition data, we have gone to using Fisher ratio on a lot of different sample types, because we can set up lots of different experiments that are class-based and find the differences between two classes of fuel. So if you're not familiar, real quick, F ratio is just a statistical moment that compares between class variants and within class variants, and really helps us find things that are very different between classes, while squashing down the things that may vary a little bit between classes, but vary a lot within their own class. And this is just kind of how you look at it in 1D, but we really care about how this works on 2D. And so our group had developed the tile-based Fisher ratio analysis, whereby you take your total tile GC GC chromatogram, break it up into tiles, but you have 4 different grids, whereby you offset them by a half tile in either direction, so that in any one grid, one compound may be more captured by one tile than it is in another. And so by taking all this information and running F ratio on it, we can generate a hit list of our best compounds that are the most different in class distinguishing between class samples. And recently you can use this kind of the interactivity with chromatograph tile. It's the outdated picture for chromatograph tile, but generally you send the same way to break up your whole chromatogram into tiles and run F ratio, and you get this hit table that looks like this, can tell you at a glance of what your best compounds are and what compound classes they're most concentrated in. And so in our group, we tried to go beyond just like finding out what compounds are, the difference between them. We're trying to do a bit more statistics on kind of the information we get off of F ratio to learn or to make better chemometric tools that we've gone through using quantification and both identification. So you can imagine after generating your hit list, we take our whole we take the whole information we find and use it to find match channels that are statistically likely to be pure, so that way we can enhance more thorough quantification, and by the same metrics we can use those to find match channels that make it easy to help subtract spectra from each other after a normalization to get very good identification. And furthermore, we've gone and applied this to trying to find a lot of polar compounds in jet fuels or rocket fuels. And so the way we thought to do that was, well, if polar compounds are going to be very extractable by solid phase extraction, and generally we just want to run solid phase extraction and see everything that comes out of there, but you may not concentrate everything, and some compounds may just be concentrated a little bit. So we thought if we can set this up as an F ratio experiment, we can find more comprehensive list of the kind of compounds that are extracted by our solid phase extraction. And so the idea was then to just run a neat fuel through a solid phase extraction and just collect the fuel that comes out the SPE cartridge and call it our pass fuel. When you run these by themselves, you don't see much different, but we can take these and run them through F ratio analysis, finding a nice list of polar compounds that are different. That's the ones that are all extracted. And we've ran through a way to kind of visualize this by taking the information from each of these F ratio points and pulling out and pasting them into like a blank chromatogram, which we call the stitch chromatogram, kind of stitching all the pieces of our F ratio analysis together so we can visualize it much easier. And so this was the kind of initial work we did on finding polar compounds in jet fuels. And well, the focus of my talk is going to be on optimizing some kind of the SPE extraction in a different way and for different phases and load volumes. We found from this that we were able to see a lot of different phenolic compounds that came out of our rocket fuels that very well associated themselves with the carbonaceous deposits. But one thing that we noticed while doing all of our extractions is that we tried a lot of different SPE phases off the bat. And what we found, here we have 2 examples. We tried using alumina and silica, and we noticed after running a jet fuel through these cartridges with the same amount of load volume, we end up with these 2 different extractions where we found, oh, the alumina had a different polar profiles than we got from the silica. And so we didn't think that silica and alumina should be so different that they pull out completely different polar compounds. And so we thought we might want to investigate this more and try and see if we can't do this to optimize a bunch of our solid phase extraction procedures, because a lot of the procedures we were following kind of told us to do this sort of high load volume on a small phase volume cartridge and to get off all your polars. But as we see, if we do the same exact procedure on two different phases, we get completely different answers, even though alumina and silica aren't that different nominally for the initial parts of the extraction. And so to try and get at this, we took our JPA jet fuel and spiked it with polar compounds, so we can kind of see the interaction of these compounds with the phase. And we ran those on two different, on alumina and silica, with all their locations of those polar compounds shown here. And we'll mention off the top the 2D separations look a bit different as we collected one of these further in the future and later went back to collect the other one, but the columns have been cut a little bit, and so we got a little bit of a different 2D separation, but we were able to match up everything in the end. And so since we think that what's going on here may be a interaction between the sample load volumes and the limited sample phase volume, we're getting the breakthrough effect, right? Where some of the compounds will inevitably be pushed off the cartridge by the overwhelming it with extractable compounds. And so in an effort to try and capture this as throughout the process, we developed a sequential SPE procedure where, like my initial study where we collected the pass fuel and compared that to the neat, we went through the entire load volume and collected pass volume in fractions. So we collected the first mill of pass fraction as a separate sample, and then collected the second mill, and so on and so forth until we went through all our 9 pass fractions. And so this gives us a whole range of samples to study and to not only discover the compounds that are changing between each fraction, but be able to track their concentration and be able to infer what their residence time on the SPE cartridges are and compare to different phases. And one thing we knew off the bat is that while F ratio is really nice and our tools work really well for this, starting to apply it to many different classes such as this gets kind of out of hand, because F ratio requires so many replicates to run, at least 3 per class, and more if you want better variance control. And so we turned to our other analysis method that our group has developed, which has been our tile-based 1v1 analysis. And this is where, whereas tile-based F ratio calculates your F ratio and requires multiple classes, the tile-based 1v1 analysis uses the unit list rank metric that is the sum normalized absolute difference of the classes, and with a little bit of algorithm to check that the data that you calculate this on is well behaved, we can get a hit list from the 1-to-1 analysis that is very well has a high fidelity to the same kind of hit list you may get from F ratio, and but only using 1 sample per class, and that enables us to do this sort of sequential analysis with many samples without having to laboriously collect data. And so that's the way we're going to find our samples. And so, but to be able to kind of visualize how the concentration changes throughout the chromatograms, we collect our samples and quantify them into what we call our concentration ratio profiles. So this is an example. If we go to one of our polar compounds that we spiked indole, and you can sum up an area around it, like either through blob detection or just through a basic tile. And then after discovering the location, you can go back into each of the fractions, sum up its concentration, and plot them all out. And then by normalizing it to the neat, where we say the neat is 1, and we can divide it all by that, we can get like a curve that describes how the concentration of indole changes in the pass fract fuel throughout the time. So what this is kind of telling us, right, is that indole starts at some amount, and then in the first mil of the pass fraction, it is pretty much 0. So there's not much signal for indole in the first pass fraction. It's been extracted and is residing on the cartridge. And that's the kind of the same throughout the first pass, next couple mils of the pass fraction. But then we see it starts to come back up, and it even shoots past back 1 mil, concentration of 1, indicating to us that the native concentration of indole or the concentration of indole in the fuel is being added to by indole eluting off the cartridge. And so we experience a breakthrough of the indole. And this is all happening throughout our 9 mil fraction volume. And so this kind of gives us our basis to see how polar compounds are interacting with this fuel in the context of the full native polar compound environment of our JP jet fuel. And so taking these concentration ratio profiles and starting off by looking at some of our spike compounds, we just want to look at how the phases differed between alumina and silica. And so I just have a couple of examples here for you to show off the kind of interactions we're seeing. And for we had a couple of the compounds, phenol, like low molecular weight oxygenated compounds that seem to extract much better on alumina. You can see that it goes to a low concentration and stays low, meaning it's resided on the cartridge the whole time and never came out in the pass fractions. But for silica, it wasn't so. It started to elute. And for some other compounds we see, such as indole, we saw earlier for alumina, that goes down and comes back up. And it does the same for silica, but the silica doesn't hold on to indole as long. And we had some of our polar compounds that just did not interact with them. So this kind of just told us that alumina and silica may not be the best to getting some of these aromatic sulfur compounds. And so the idea we kind of came to with seeing this sort of effect is that many of the polar compounds are kind of competing with each other for extraction sites or binding sites on the SPE cartridge, where phenol in alumina anyway is very that never comes out, so it has a pretty high affinity for the alumina cartridge, whereas indole starts off with being extracted, so it has a high affinity, but as we keep going on, we keep putting on more and more compounds from the input of fuel that have higher affinity, and so all the high affinity compounds will start pushing off the compounds that have lower affinity. And we kind of see this effect as the breakthrough throughout time, throughout the extraction procedure. And after understanding that sort of phenomenon with the spike compounds, we went ahead and looked at our 1v1 analysis to find out what is the difference and how is this affecting native polar compounds in our fuel. And so we put together a list of the top differences in our 1v1 analysis hit list of our neat fuel versus our 1 milliliter pass fraction. After seeing what we saw with our spike fuels, we thought the best way we can get capture everything that is changing is to find it within that first mil when most of the cartridge has not been filled up yet. And so taking that list, we slim it down to only focus on the compounds that change with concentration ratio less than 0.5. So that means that they decrease by at least half into the first film pass fraction. And so what we find, we plotted all those here, and so we can see, despite like the little 2D chromatogram differences, we have most of our polar compounds extracting in some of the similar areas. And so that's in contrast to what we saw earlier with the extract, where alumina, we definitely saw some polar compounds coming off in this region, but we did not see them in that region in the silica. But when we look at the first mil pass fraction, it says silica should still have those compounds coming off. And so that may be telling us that, well, yeah, obviously silica and alumina, while they're not so different in their initial extraction, later on throughout the extraction process, so all of these do not have as much, all these compounds here don't have as much affinity for the cartridge and get pushed off by later other compounds. And so in in an effort to kind of compare these to each other, we can take all these compounds we discovered and plot their concentration ratio profiles and get an overall view of how the extracted compounds behave with both alumina and silica. And so overall, it seemed that alumina seemed to hold on to compounds for a while longer than silica did, where most of the compounds that were being extracted by silica and detected by our 1v1 hit analysis method eluted within the first fraction, with save for some of these compounds that stayed down the entire way. And that was very interesting to us. It kind of told us that for some of the initial compounds, that alumina seemed to be a better extractor of the phenolic compounds, whereas silica was being more selective for other things. And this is not something you would maybe notice if you're just following a SPE procedure where it tells you maybe take your cartridge and run 20 mils of fuel through it and then elute out with methanol, dry under nitrogen to dryness and reconstitute. Here because you see if you go through both of these towards the end, you're going to get a totally different amount of polar fractions coming off, even though that they extract somewhat similarly towards the beginning of their procedures. And so to kind of just bring this all together and look at it in more of a PCA kind of way, we wanted to submit all of our different concentration ratio profiles that we just saw there to PCA. And so we just submit it in this way where every profile was its own sample. And that just, and it shows us that alumina and silica separate out nicely, which is something we kind of already told a little bit visually by looking at them, where alumina kind of spread out more over here and silica to here. So based on what we saw, that can tell us that these samples more extract down and stay down longer, and where these ones kind of extract down real quick and then return to the concentrations really quickly, with the save of a couple of the silica compounds that did extract and remain extracted. But this doesn't really tell us, this kind of told us an overall view of how alumina and silica may interact with this specific jet fuel. But we also wanted to know how each of the compounds individually kind of spread out amongst these phases. And so that way you can kind of get like a matrix of how a compound is affinity might play out for both silica and alumina. And so you can then organize PCA in a different way. Instead of putting all your concentration ratio profiles as their own samples, you can match up your concentration ratio profiles for the same compounds, augment them, and submit those into PCA. And so when we do that, we end up with a distribution like this, which doesn't really mean much when you look at it, but if we can then match up each of those compounds to their identities, we can get some trends coming out of this. And so very broadly, what we found is that for our phenolic compounds, on the left side here, these are compounds that extracted really well and stayed extracted throughout most of the concentration on alumina. And as we go to the right, the affinity for alumina decreases. So over here, they re-eluted off alumina sooner than compounds over here. And we see that those phenolic compounds tend to be ones that have where their phenol group is more unhindered by their sort of alkyl groups. An example here being this 2,3 diphenyl dimethylphenol. Has very high extraction affinity. But if we go over here to the other side of PC1, we have another a 2,6 dimethylphenol, same amount of alkyl groups, but it does not, but it gets eluted off the alumina cartridge much quicker. And so that's something that's very important to kind of look at. And so when now that we have this kind of idea, we can spread apart and I can see, okay, so we have this alumina being and silica have a breakthrough of our phenolic compounds for high load volumes, and it seems to favor the compounds that have unhindered phenolic moieties. And so just taking a look at that at the end, we can take a compare their concentration ratio profiles, so we can kind of convince ourselves of that. Like looking back at that 2,3-dimethylphenol, yes, it extracts. See that play out with the trimethylphenols as well. Comes out low and elutes high, and that played out well for some of our other compounds, such as sulfolane, that actually is the only one that really extracted well in both alumina and silica. And so this kind of gave us a way to determine what sort of phase you might want to choose for your extractions of jet fuels and or rocket fuels, and how to balance the sample load volume. And maybe we can even investigate this further by checking out different sorts of extraction phases, such as fluorosil or the other brands of alumina. We use alumina N in this case. And so we demonstrated that under the general typical SPE conditions, you have a lot of limited absorption capacity, which ends up in breakthrough in the general way that you might use SPE. Alumina seem to be a lot better for the extraction of phenolic compounds from this fuel. And later on, we hope to kind of use this to select our phases more efficiently to get a more comprehensive picture of our polar compounds, so that they can further inform our studies on the thermostability of fuels. So that way we're not missing any important details. And with that, thank you for your attention, and I'm happy to take any questions.